Unfortunately, you guys are going to have to listen to me for a little while. Okay? So, just to give you sort of an idea, things that you can expect. There will be days when you're going to have to do a lot of listening to me. There are going to be days we're going to do like zero listening to me. It's going to kind of.
What's the day?
I like to say that physics and notes in physics is kind of like bananas.
Are we taking notes today?
They come in bunches.
You didn't answer my question.
I know. I wouldn't call these notes. This is sort of a flow chart. I don't give a ton of notes. In fact, I'm not a huge believer in you writing everything down, especially when I'm going to post it later anyways. Although I think that sample questions are a good thing to write down and sort of get to that process. So when we get to sample questions, I sort of stress a lot more, but we're sort of doing just notes. If it works better for people to just listen, then that's fine with me. Okay? This is kind of a workbook, I guess you could say, that we're going to work through together. Then you're going to do some practicing at the end. Hopefully in time, I'll be done before you guys are ready to leave. Okay, so again, a good thing to have is like a pencil or a highlighter, because I'm going to get to a point where I'm going to say, yeah, you need to do that, and then if you're going to have to spend 30 seconds then getting it ready, then that's going to be, right? So might as well get it ready now. So we're going to spend some time today talking about graphs, because graphs are really important. Graphs can sort of help you understand the relationship between different things. You're going to be doing graphs in any labs that we do. So I wanted to sort of make sure that everyone's sort of got the same baseline skills when it comes to graphs. Okay, this 3-man table is only going to work if you guys are here. It's now 1:14. I've given you plenty of time to get in and get settled, but now it's my turn.
Focus.
He's actually right there. Okay, so displaying data with graphs. After this, you'll be able to create a graph, interpret a graph, including the meaning of the slope, recognize a linear, quadratic, and inverse function. A well-designed graph is more than a picture worth 1,000 words. It can give you more information than either words, columns of numbers, or equations. To be useful, however, a graph must be drawn properly. In this section, we'll develop the use of graphs to display data. Now, I know that you guys have all done graphs before, but again, I'm just sort of making sure that everyone's got sort of the same baseline skills. So we're going to use an idea that you probably looked at in grade 10 science, the idea of braking distances, right? It's something that you're sort of kind of familiar with that also ties in with physics, right? So when driving, there are two parts to the total braking distance. They are reaction distance and braking distance. So let's just take a moment to define those. So what would you call the reaction distance? How long, Brandon, do you mean like the time, or do you mean the distance? Because I know that we Canadians tend to measure distance with time. Like, how long is it? How far is it to Brandon? Oh, it's like 2 hours, right? But that's not really.
How far it takes you to put your foot on the pedal.
How far it takes you to stop when you put your foot on. Like how far your vehicle travels while you're stomping on the brake. Yeah.
That's the reaction distance?
While you're like, oh, treat, that's like under 100 meters.
That's what you're telling me is the braking distance. Yeah. This is the
like once you press the brake.
Distance traveled while foot on brake. Right? The braking distance is the distance traveled while your foot is on the brake. Right? And the reaction distance, someone said it. I've never heard it put that way before, but what would I change? I'm just going to copy this. What would I have to change here? Well, besides making it smaller. Before or while putting your foot on the brake? Then it becomes braking distance. That's right. The distance traveled while putting your foot on the brake. So the distance you go in the time it takes to go from, oh, got a brake, and foot actually hits the brake, right? Which one of those would be less? Reaction would be probably significantly less. Should be. If you're paying now, is everyone's reaction distance going to be the same? No, everyone has different reaction times, and it depends on a variety of things too, right? Whether you're paying attention, your sobriety, just your general fitness, lots of different things. Okay. So you should know the difference between those two things. Now, this table here shows both based on various speeds. Now, generally, physics students work in meters per second, but cars we talk about cars traveling in kilometers per hour. So I need to remind you how to convert. Do you remember the magic number 3.6? 3.6 is the magic number to convert from meters per second to kilometers per hour and backwards, okay? So how do I go from meters per second to kilometers per hour? And the answer is multiply by 3.6. So 10 times 3.6 is going to be 36. You guys do the rest. Okay, so what do you got here? 15 times 3.6, I think it's 52, am I right? 54? 20 is like 72, 25, 98, 90, 108. Okay, so if you're driving down the highway at 108, I don't even know how fast that is, my car doesn't go that fast, you'd be going 30 meters per second. How far is 30 meters? Heads up, Zane, coming towards you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 rooms. In other words, the entire length of that hallway there per second. I dare some of you to go out in that hallway, close your eyes, and run down the hallway.
That's a bad idea.
But yet you do it on the highway when you kind of look at your phone.
Huh.
Just saying.
Funny how that works, eh?
Or even if you're just, playing around with the stereo or something or other, right? Or 1 second, 30 meters. Just pointing that out. Do I? I'll look at it from time to time. But I certainly don't do this.
Yeah, you reply to one hand.
I have the Bluetooth in the car riding my first on.
No, see, this is why you gotta memorize your passcode. Like, without looking at it.
Or you should figure
Just ignore it. I'm not that popular,
I
Cole.
think you have to watch. You have to
Yeah.
look like that.
Anyways, moving on. Okay, so I need to make this a little bit smaller.
You doing this?
Okay, you guys are getting off track again. Back, you're getting off track. Okay? I need more than 3 or 4 minutes of attention time. Okay? So in our example, the speed of the car is the independent variable or the manipulated one. That's something that you should know. Independent. The independent one is the manipulated variable. The variables, the other 2 variables, reaction distance and braking distance, change as a result of the change in the speed. These quantities are called dependent variables or responding variables. 99% of the time, we put the independent where on the graph? It's the X, the bottom. And the dependent, the one that you measure, is on the Y. Sometimes we do it opposite just because one is easier to measure than the other. But it depends on what you're trying to do. Okay? So, how do the distances change for a given change in speed? Notice that the reaction distance increases by about the same amount for each increase in speed. So, actually, if we go back to this here, right? The reaction distance, this is going up by how much each time?
3.
Yeah, 3.7 here, I guess, right? 3.6, 3.7, maybe it's a rounding thing. So it's kind of going up by the same amount each time. But you will notice that the braking distance, this goes up by like 11, 16, 21. It's going up by more and more, right? Where does this total distance come from? Yeah, add them up, equals, right? Equals. Now here's an interesting little thing. Depending on what your reaction time is and your quality of your brakes, you can travel up to 104 meters, the entire length of the football field, if you're doing 108 on the highway just to stop. That's a long ways, right? It's kind of why you're supposed to kind of be looking ahead. you're, not just down in front of the car, looking ahead as you're driving.
Yeah. What about like braking coefficients and stuff too?
Oh yeah, I mean that's very generic, absolutely. Yeah. How do the distances change for a given change in speed? So I said this already. Notice that the reaction distance increases by about the same amount for each increase in speed. The braking distance, however, increases much more as the speed increases. The relationship between the distances and the speed can be seen more easily if the data are plotted on a graph. To avoid confusion, you should plot two graphs, one a reaction distance and the other braking distance. So I'd like you to label these down here. So the blue one at the bottom, this one is, and I'm going to abbreviate, this one is the reaction, RxN, reaction distance, that's the bottom one. And this red one here is the braking distance, BRK. And the green one here is the total. And you'll notice that the shape of the graphs are different. Right?
Yeah.
The reaction one is a straight line, but the red and the green ones are curved, right? And in fact, if you add this, this thing there, it should be the same amount as that. It's not quite, but it's close. It should be, yes. Okay, so here are the steps for plotting graphs. And I know that you've been taught how to do this likely in junior high at some point, right? So just a refresher. And you're going to be plotting some graphs in a bit here. These steps will help you plot graphs and data tables. So identify the independent and dependent variables. Figure out which one is X. Figure out which one is Y. Put the Y on the vertical. The independent variables plot on the horizontal, or X, and the dependent variables plot on the vertical, or the Y. In our example, speed is plotted on the X, and the distance is plotted on the Y. Determine the range of the independent variable to be plotted. What does the range mean?
Side to side.
What do you mean, Kyle?
Farthest distance from side to side.
Pardon me?
Yeah. That's like
Okay. Yeah, well, in math, they talk about range and domain,
yeah,
right?
yeah.
And they kind of mean the same thing. Domain is for x's and range is for y, right?
Yeah.
So we're using range in the non-mathematical sense, but very similar. The range is simply how big, what's the smallest value, and what's the biggest, and like make sure that it fits in your graph. That's kind of what I'm saying. Exactly. So determine the range of the independent variable. In the above example, data are given for speeds between 10 and 30. So what they're suggesting is, here's the range from 10 to 30. If you can include 0, should you?
Yeah.
Yes. 0 is sort of it's a good benchmark. It's a good thing to sort of know. So if you can include 0, you should. So in this case here, we're going to go from not 10, we're going to go from 0 to 30. Okay? Decide if the origin is a valid data point. That's important too. Is 0, 0 a data point? Well, in this case, we didn't have that in the data, but if you're traveling 0 meters per second, what's your braking distance? 0, right? So is that important to know?
Yep.
Yes, so you should include it. And we did. Spread out the data as much as possible. Let each space in the graph paper stand for a convenient unit. Choose 2, 5, or 10 spaces. Don't, if you've got a big giant piece of paper and you only need to do one graph, don't scrunch it down into 1 square centimeter. Why not? It's hard to read and it's not very accurate, right? Make it a good size. Number and label the horizontal axis. Now I'm going to tell you this right now. Some of you are going to lose marks on the test because you don't label. The axis must be labeled. I expect that. Repeat steps 2 to 4 for the dependent variable. Plot your data points on the graph, and this is important too. People will lose marks for this. Draw the best straight line or smooth curve that passes through as many data points as possible. Do not use a series of straight line segments that connect the dots. Do not connect the dots. Do not connect the dots because we are interested in the overall trend. Okay? So now this one here, if you look at this one, well, it forms a perfect straight line, right? Have I connected the dots? Sure I have. But I didn't mean to do that. I just drew a nice straight line, right? Sometimes your data is not going to be perfect. I don't want this. That doesn't help me. Okay? You put a ruler on and you estimate what's the line of best fit. What's the line that best represents that data? Yeah, I kind of missed when I drew it. I didn't do a very good job of it. Make able to fix that, can I? Let's do that again. Like that, right, Brett? Yeah, that would be better. Okay? I'm going to show you how to do that on Excel and use statistics to do that, right? When you're just doing it by hand, you just literally estimate. Okay? But do not connect the dots. Give the graph a title that clearly tells what the graph represents. In other words, I'm looking for a title on the test, like this. Label the graph. I want labels. Okay. The graph figure 2 of reaction distance versus speed is a straight line. That is, the dependent variable varies linearly with the independent variable. There is a linear relationship. Why linear? Because it forms a straight line. Got that, Jonathan? The relationship of the two variables shown in this graph can be written as an equation. Y equals mx plus b. Remember that stuff?
Yeah.
That's lots of fun. Y equals mx plus b, where m and b are constants called the slope and the y-intercept respectively. What does the word respectively mean in that situation? It means in that order. So the m is the slope, right? So they go m and b, slope and y-intercept. So that means that the m is the slope and the b is the y-intercept, right? Have you all calculated slope before? You should have. Okay, here's how to find the slope here. M is equal to rise over run, right? Delta y over delta x. So now where did these numbers come from? From the graph, some data point, right? So what data point are we talking here? Well, in fact, if you go back, you've got your data there right in front of you. If we go back, we're going to use, I think, 25 and 10 were the two data points. We're going to pick these two data points. It doesn't matter why. You should pick data points that are either on the line of best fit or the closest ones, right? Or points that are right on the line, I guess I should say. So in this case here, we're using this data point there and this data point right there, right? And I'm just going to take some. Oh, I didn't mean to do that. Quite like that. Let's erase that so we can see better. I'll get rid of this one here too. Okay, so let's pick these data points right there. How do you find the slope? Okay, here's a review for you. It's delta y over delta x, y2 minus y1. So which one of these is the y2? The one on the left or the one on the right? Right, so the y2 is this number there, which in your data table is going to be 18.5. That's your y2. Right? This data point here is at 25, 18.2, and this data point here is at 10 and 7.4, right? X is always first, right? X and then Y. So you can take the difference in Y. So 18.2 minus 7.4 over top of change in X's, 25 minus 10, 18.5 minus 7.4 is 11.1. 25 minus 10 is 15, and when you divide, you get 0.74 s. 0.74 seconds.
So would that be like the difference in reaction time?
You're on the right track. That's what my next question is right now, is what is that time? What is the 0.74? It says underneath. Notice that the units have been kept with the variables. So on the top here I've got, and this is one of the key things you're coming out of this today, because this is distance over here, this is in meters, and I didn't label that. This is in meters, and this is in speed, meters per second. And when you divide those meters cancel, and you're left with seconds. The slope is measured in seconds. 0.74 seconds is the slope. So what is the value of the slope? It is a time. It is the reaction time. This person has a reaction time of 0.74 seconds. It's the time that the body of this person takes from the instant the message to stop the car registers in your brain until your foot hits the brake pouch. This person takes 0.74 seconds to get foot from gas to brake. Is that a good reaction time?
That's pretty, that's 0.04 seconds.
Less than a second.
0.7.
I get 0.2.
Alright. We did
Did you do that thing with the ruler? Yeah.
Left foot braking, that's what.
That was like,
Ooh, bad idea.
that was like 0.13.
Yeah.
Or like, no.
It's probably not the best because people are like, you know, they're waiting for it, right?
Yeah.
It's a measure. 0.74 seconds. But the key idea is this, you guys.
That was like 0.2.
The key idea is this. The slope is a property of the system. In other words, in math, they don't teach you this. Generally. In pre-calc, certainly not. In applied, maybe so. The slope means something. It has value. It's some characteristic, some property. In this case, it is the reaction time. I'm going to be asking you what's the meaning of various slopes. Okay? So it's not good enough to be able to just calculate it. Okay, now what does this y-intercept mean? I'm almost done. I need about 8 more minutes of your time. And I'll be quiet. The y-intercept B is the point at which the line crosses the y-axis and is the y value when the value of x is 0. It is this point right here, right? That's the y-intercept. It's the y value when x equals 0. The y value when x equals 0. In this case, when x is 0, the value of y is 0 meters. If we go back to this one, what's the y-intercept? 0, because if I'm going 0 meters per second, my reaction distance is 0. I'm already stopped. This is just an example here. The value of y does not always increase with increasing x. If y gets smaller as x gets larger, then delta y over delta x is less than 0, and the slope is negative. This is an example of negative slope. Right? Just kind of reviewing all these ideas from math here for you. Okay, quadratic relationship. The graph of braking distance versus speed is not a straight line, but rather looks like a parabola. Have you ever heard that word before?
Yeah.
No, that means
Yeah, sort of. It's that curve, that x squared shape, right? There's actually several arches. If you hang a chain, that's called a catenary arch. It's not actually a parabola. If you hang a chain will just, or a rope will just form that shape. It's also the shape like in a Roman arch, like a bridge kind of thing. This indicates that the braking distance varies as the square of the original speed. In other words, if you double your speed, the braking distance increases 4 times. Jonathan, you with me there? The graph slope changes so it cannot be calculated. Can you find the slope of a curve like this?
Yeah. No.
Because it's changing all the time, right? You can, however, calculate the slope of the curve at an instant by drawing a tangent line, and I'm going to talk more about that in a little while. Question, if it takes a person 40 meters to stop after driving at 50 kilometers an hour, how far will it take them to stop if they're driving 100?
80 meters.
I hear 80. Anyone want to offer an alternative answer?
should be double.
It's going to be more than 160.
160. How'd you get that one? Why'd you do that? Because it says it right there. Way to go, Crady.
Oh.
Because he was paying attention. What do you know?
Loving it's a present now.
Have a cookie.
That was
It's 160. How come? Because it's 4 times. It's a squared relationship. You're welcome. It's a squared relationship. It says it right here. The braking distance increases 4 times. Which is why, if I'm driving at 100, and you're driving at 110 kilometers per hour, that's a 10% increase. You're going to take 21% farther distance to stop. 10 kilometers more an hour is a 21% increase in distance. Just saying.
Does that include the reaction time in there?
No, that's just the braking distance. It's actually more when you include reaction distance because you're going to be going farther in the time it takes, right? If we have equal reaction times, you're going to be going so almost 25 seconds.
At 100 kilometers an hour, it takes like 80 meters to stop. At 110, how long?
It would be like 80 meters times 1.21, so about a little over 100. Yeah, it's got to do with kinetic energy.
Oh, that's tough.
Grade 12. You've probably heard of kinetic energy. Okay, almost done because I know you're getting antsy. Inverse relationship. Some relationships are such that as one quantity increases, the other decreases. As something gets bigger, the other thing goes down. Like, for example, attendance versus marks. There's an inverse relationship. This is called an inverse relationship. Its graph would look like figure 5. Sometimes it's an inverse like this, sometimes it's a straight line. Again, you can only determine the instantaneous slope by applying the tangent line method. So I basically reviewed with you everything you learned about graphing, probably from pretty much about grade 4 to grade 10, really, in the last 20 minutes. Right? So here's a concept, a little review. I'm going to give you a chance to work on this. I'm going to give you, how many questions are there? There's 4, right? No. I'm going to start with 12 minutes. And we'll see how far you are. Mainly because I know that people have trouble with this and they need help before they move on. So I'm going to set a timer for 12 minutes and see what happens. Okay, so we did question number 1 already. If the y-intercept was 3.4, it would mean that even though you're going 0 meters per second, you still have a reaction distance, which doesn't make any sense at all. This is impossible. Someone messed up here, right? Sometimes the y-intercept should be 0, and sometimes it definitely should not be. Okay, in the breaking example, at what speed is the reaction distance 10 meters? So this is, and I need to label this, Leo pointed that out, this is distance over here, and this is speed right here. So when is it 10 meters? About 14 meters per second, 13 meters per second, something like that. Right?
What about me here, Slav?
About 14 meters per second. Okay, number 3. So these guys can go. A graph of reaction distance versus speed is made, and the slope is found to be 0.74. Suppose that another experiment is made. So here's the slope, 0.74, and it's found to be steeper. Okay, steeper meaning like this. So first of all, numerically, what would be a possible slope value for this?
20.
This is 0.74, like 0.9. And remember, this slope is 0.74 seconds, so that's going to be 0.9 seconds. So this means, Cole, I'm doing this for you.
It will be slower.
This means that it's a longer reaction time, which means that the person's reaction time is slower. Maybe they are
Intoxicated.
or some other type of disability. Okay. Number 4, listen carefully. I'm going to stop talking in about 3 or 4 minutes, so listen carefully. Figure 6 shows the relationship between the circumference and the diameter of a circle. So first of all, I hope you remember diameter is the distance across, Ty.
Radius.
You're still learning here. Yeah, and the circumference is the distance all the way around. Okay, so would a different circle circumference create a different graph? And the answer is an emphatic no. You guys don't understand what this graph shows. How many circles are already shown on that graph?
5.
At least 5. At least. These are circles with a diameter of 1, a circle with a diameter of 2. These are all different circles. Diameter 3, diameter 4, diameter 5. And I would argue all of those numbers in between as well. It's an infinite number of circles.
Infinity.
So no, if you had a bigger one, all that would happen is the line would sort of continue on forever, right? What are the units for the slopes? Well, the y units here are centimeters, and the y units here are centimeters. And when you divide, because that's what you do, y divide by x, centimeters divide by centimeters, what do you get? You get nothing. Not even 0. You get nothing.
How do we know that there's
You're right. You're right. I mean, those data points are there, but you could certainly, that's called like interpolation. So if you had a circle, if I asked you if there was a circle at 1.5, you could estimate it, right? So while those data points haven't been measured, another circle would fit in there, right? Like it's not a gap. That kind of answer your question?
Yeah.
Yeah. Okay, so the units here are nothings. Now, the value of the slope. You are supposed to calculate the value of the slope. A couple people ask me, does it matter which points I pick? And the answer to that is no. And I'm going to, on purpose, not pick the two outside ones that everyone always does. Here's how you calculate slope, right? Delta y over delta x. What's the y value here? What would you call that? It looks like it's right in the middle. Should we call that 12.5? It's between 10 and 15. Subtract, and what would you call this one right here?
6.
Okay. And the x value here is 4, and the y value here, or the x value here is 2. So 12.5 minus 6 is going to be 6.5. 4 minus 2 is 2. My answer is 3.25. 3.25 what? No, there are no units for this slope. We just did that in B.
So what is it then?
There are no units. It's just 3.25. I did trick you. Now think long and hard about this. I'm giving you some free thing here. I know you're in a rush to go. Okay? It's 3.25. When you're talking circumference and diameter, what's also in that formula?
Radius.
Circumference. Do you guys know the... Is not the formula circumference is equal to pi times diameter?
Yeah.
Right? Okay, now, do a little bit of algebra here. If I divide both sides by d, what happens?
Circumference. And
Circumference over diameter is
pi.
equal to pi. Right? Circumference over diameter is equal to pi. And if you look at your graph here, and I'm going a little faster than I want to, if you look at the graph over here, what's the y quantity? Y divided by x. So when you take y divided by x, c divided by d, you should get... What's the value of pi? 3.14. How come I didn't get 3.14? Because it's not exact, and we estimated those values, didn't we? Okay? So, the answer to part D, what is the meaning of the slope? Previously, one of our meanings was reaction time. Here, the value of the meaning is the number pi. Which is why, if you had a different circle, you would get the same, it would just be a graph beyond that graph. The value of the slope would be pi. Whew! Okay. I would like you to do, you've got a little bit of time left here with these guys though. At the very least, you need to get number 1 done for tomorrow on the back. Okay? Get as much as you can done on the back. You guys can work on the bus, right?
Yeah, for sure.
I'm texting Mr. L.
Yeah, one of them
Probably die.
Who's got them on their Googler?
I did.
Do you? Google up.
Like Google what up.
Tell them? Well, text them and say, you didn't even focus in. Holy moly. You got a lose.
Okay, I'll call back.
No, yes, so you need to-
Oh, wait, I'm gonna find my friend.
Does that strike you as odd, Sarah? Please do those graphs at the back. You guys have some time. They get, number 1's real easy. All you're doing there is reading graphs. You guys should be able to get 1 and 2 done. Okay? You guys do 1 and 2 for tomorrow, and then I'll give the answers, and I'll give you a chance to work on number 3 tomorrow. Okay? We'll do 1 and 2 for tomorrow. Okay, so number 1. The graph shows the mass of 3 substances for volumes between 0 and 60. What is the mass of 30 cubic centimeters of each substance? Now, do I happen to have this on the next page here? Because that would be awesome if I did. Right there, right? So 30 centimeters cubed of each substance. So you just simply go that point, that point, that point. So what would be your answers? It looks like about, what would that be? About 50, maybe 55? Approximately 55? Right? And then 30 cubic centimeters of this one looks like it's just under 100. About, well, I'm going to say 90 because I think that line is 80 there, isn't it? Each line is 20? Yeah, so then that means, oh, it's just under 100. So maybe 80, 90. 25? 30 is right here, Cody. Easy, easy. Okay, so then 30 here would be exactly right there. That would be, oh, they're not 20, they're 25, aren't they? They're 25, so that's going to be 150. So let me go back to this one here. If that's 25, then that's 75. Okay, maybe 85, 85, something like that. Okay, as long as you're ballpark close. How would you make sure, okay, you guys with earbuds in need to take them out. How would you make sure, like if you're not sure on a test, you want to show me that you understand how to do this? What would be the way to show me that you get it, even though your number might not be exactly the same as mine? Yeah, draw lines, circle them, indicate somehow. Jonathan, you need to watch. Indicate somehow that you know what's going on. Okay, if I had 100 grams of each substance, so I'm going across from there. So that one is 20 cubic centimeters. This one's going to be like, yeah, 30, I'd say, well, that's 30, that's 35, so 33. And then 100 would be right there, that would be 50. I expect you to be able to do that.
Oh wait, no, I got
You're
it.
just reading the graph. Yep. What are the units of the slope of the graph? How do we find the units of the slope? You look at the y units. You look at the x units. The units of the slope are going to be grams per cubic centimeter. The units for the slope are grams per cubic centimeter. What is the value of the steepest slope? They're asking you the value, they're asking you the number. Pick two data points. Any two. I don't know what I'm going to get. We're going to find out here. So that data point there is going to be right at 200, right? So it's going to be 200 minus this one here is going to be at 50, which of course is 150. And this x here is 40, and this x here is 10. So we get 150 over 40 minus 10 is going to be 30, and 150 divided by 30 is not 50. 5. 5 what? I'm not done. 5 grams per cubic centimeter. And what is the meaning? What do we measure in grams per cubic centimeter? What is mass over volume? Did anyone get it? It is density. The meaning of the slope is the density. Okay? Every slope has a meaning. Okay. Well, I don't know about that. You're going to do numbers 2 and 3 tomorrow in class. Okay?